Okay, so this is just part 3 of our notes on determining if a molecule is polar or nonpolar. And so we did some examples here with CO2 and water. I'm just going to show you a few more examples, and we're going to use those 3 criteria that I showed you in the last video. Okay, so this is part 3. So we'll start with ammonia. Ammonia is NH3. And for all of these, you have to draw them. So unfortunately, there's no easy way here. Okay, nitrogen goes in the middle. Hydrogen never goes in the middle. Each hydrogen has 1. Nitrogen has 5. Okay, so this is my ammonia, NH3. I have 3 single bonds and 1 lone pair. And so because I have 3 single bonds and 1 lone pair, that means that this is trigonal or trigonal pyramidal. So just remember, it's really difficult for me to drive my tricycle up the pyramid. Okay, and so with 1 lone pair, it's trigonal pyramidal. And so if we were to draw it, we should show it kind of looking like a pyramid if possible. Okay, and then we can look at our electronegativity numbers from the periodic table. Nitrogen is 3.04 and hydrogen is 2.2. So I can draw a dipole moment. That's that big arrow, and the big arrow goes from the low number side over to the high number side. So this is what my dipole moment looks like for ammonia. It goes from the low numbers over to the high numbers. If you can draw an arrow from the low number to the high number, then you know for a fact that it's polar. Okay, what's another nice, easy way to know that it's polar? Criteria 1, lone pairs on the central atom. Okay, so because nitrogen had lone pairs, that told me, without having to draw it, that it's polar covalent. Okay, the next one is ClF3. Okay, chlorine goes in the middle. Start with the outer on the outer first. So each fluorine has 7, and then chlorine has 7. 1, 2, 3, 4, 5. It should have 7, so I have leftovers. So I need a lone pair loop. So here I'm showing that I have 3 single bonds and 2 lone pairs. Even though I don't have this circled, it's still a lone pair. So this is 5 domains, so it's trigonal bipyramidal. If it's tri-bi with 2 lone pairs, that's C the line. So C the 2 lone pairs is T-shape. So it should be T-shape. And that's pretty much what we're showing here. Okay. Now, because lone pairs repel more than bonded pairs, it will just slightly push these away. And because fluorine is 3.98 and chlorine is 3.16, we can draw a dipole moment from the low number over to the high number. Anytime you can draw an arrow from the low number side to the high number side, then it's polar covalent. And we're talking about the whole molecule. Okay, so this is a polar covalent molecule. What's another nice, easy way to know? Lone pair or lone pairs on the central atom. Okay, our next one is CHCl3. And carbon always goes in the middle. This is 1 carbon, 1 hydrogen, 3 chlorine. Kind of make it like a cross, okay, like a cross. And hydrogen will never go in between anything because hydrogen has to have 1 lone pair. I'm sorry, 1 bond. No lone pairs on hydrogen, just 1 bond. So hydrogen has 1. Each chlorine has 7. It's a good idea to start with the outer on the outer first. And then carbon has a total of 4. Okay, now this has 4 domains, so this is tetrahedral. Tetrahedral with no lone pairs is tetrahedral. So this is a tetrahedral shape. If I put my numbers in, and you really don't need to worry about the number in the middle for the most part. You could put it in. It'll still work out the same way. Can we draw an arrow from a low number side over to a high number side? Yes. We can draw a dipole moment from the low number over to the high number side of the molecule. So that means this is polar covalent. So the molecule is polar covalent. What's another nice, easy way to know that it's polar covalent? If the elements around the central atom are different from each other, then it's polar. So I had here hydrogen and chlorine. Hydrogen and chlorine are different from each other, so that tells me this is a polar covalent molecule. Okay, our next one is methane, CH4. So each hydrogen has 1. The carbon has 4. We have no lone pairs. Carbon never has lone pairs. That might help you out a little bit. So no lone pairs. And we have 4 single bonds. So it's tetrahedral, tetrahedral. And if we were to put our numbers in, we don't have one side of the molecule that has higher numbers than the other. So we can't draw a dipole moment. That tells me this is probably nonpolar. How do I know for sure? I can look at my 3 criteria. Okay, so my 3 criteria are lone pairs on the central atom. Carbon never has lone pairs. Elements around the outside that are different from each other. Nope, they're all hydrogen. Do I have only 2 atoms of different elements? Now, in this case, I actually have 1, 2, 3, 4, 5 atoms. Okay, so I don't have lone pairs, criteria 1. I don't have elements around the outside that are different from each other. They're all hydrogen. That's criteria 2. I don't have only 2 atoms that are different. Because I don't have any of those 3 criteria, then it's nonpolar covalent. Okay, and the last one's HBr. Okay, now this one's a little bit tricky. We don't really have a central atom here. And we only have 2 atoms together. Anytime you have only 2 atoms, it has to be linear. Okay, no way around it. If you have only 2 atoms, it's always linear. So, if we put our numbers in, hydrogen's 2.2, Br is 2.96. Do we have one side of the molecule with higher numbers than the other? Sure. Bromine is higher than hydrogen, so we can draw a dipole moment. What's another way that to know this is polar? This was criteria 3. Only 2 atoms of different elements. Okay, so if we look at our criteria, only 2 atoms of different elements. That's why HBr is polar.